Hi there folks, this is the Unit 7 review, and as always I am the amazing Mr. Jansen, so away we go. If we look at these first two, they're asking us to solve each of these, and we're going to go always to our most basic method for solving these. We're going to look for a common base that we can get here. The thing that we tend to do is we overthink these and we start to use logarithms. You could solve these using logarithms, but it's much easier to recognize the 4 and 8 have a common base of 2. 4 is 2 to the second power. So I can rewrite it that way. 1/8 is 2 to the negative third power. And again, think of it this way. 2 to the third power is 8, so 2 to the negative third power is a 1/8. That's what negative exponents do. And now here I multiply the exponents. That's going to give me a 2x plus 2. Well, now since I have the same base, I just set the exponents equal to each other. So this one would be a 2x plus 2. Over here I just have the negative 3. I set these equal to each other, and now I just finished solving this thing. So I subtract the 2, and then I end up dividing by the 2, and that's it. So I end up with a negative 5 halves for this one. Okay? So again, look for common bases when you can. That is by far the easiest method for these. Alright? Same thing with the next one. The next one, I can get a common base of 3 here. So 27 is 3 to the third power. 9 is 3 to the second power. And now from here, I multiply the exponents and I set them equal to each other. So again, I'm going to be distributing these exponents. Because that's my properties of exponents, when I raise something with power, I multiply them. But now the same base, I set the exponents equal to each other, so I end up with a 6x plus 24 equals the 4x minus 8. And now I just have to get all the x's on the same side. I'm going to subtract the 4x from each side. I'll also go ahead and subtract the 24 from each side to bring that guy over here. So when I do this, I end up with a 2x equals a negative 32, and now I divide each side by the 2. So x equals a negative 16, and that's it. If I take a look at the next couple, it's asking me to rewrite each of these as a single logarithm. So using my properties of logarithms, I start by following order of operations. So right away, the 3 that's right here, that's multiplication, so I'm going to take care of that multiplication first. Multiplication becomes an exponent inside the logarithm, so that goes up here as an exponent. So it becomes log base 2 of x plus log base 2 of y to the third minus log base 2 of 5. Now between addition and subtraction, those are tied, so I just go left to right. So I do the addition here. Addition becomes multiplication inside the logarithm, so it becomes x y to the third inside the logarithm. And now the subtraction becomes division inside the logarithm, so it becomes log base 2 of, that's going to be an x y to the third over 5. And I just write that inside of one single logarithm. And that's it. And the next one, again, I start off the same way. The first thing I see here is that 2 that's out front. That's going to go up as an exponent, becomes an exponent inside the logarithm, so it becomes log of 5 to the second, which is 25. Inside the parentheses here, I'm going to go ahead and do this addition. Addition becomes multiplication inside the logarithm, so it's going to become log of xy. And now I can take care of the subtraction. Subtraction becomes division inside the logarithm, so it becomes log of 25 over xy. And we'll notice that there's no base written for this logarithm. That means it's the common logarithm that's log base 10. All right, which doesn't really affect us in this particular example, but it is important to know that. Okay? If I look at the next one, it says to expand, so I'm going to use the same rules I was just using, but I'm going to use them in reverse. So the division that I have inside the logarithm, I'm going to split that into 2 logarithms being subtracted. And now from here, the first logarithm has multiplication inside of it. Multiplication can be rewritten as 2 logarithms being added, so it's natural log of 3 plus the natural log of x. Over here, the exponent inside the logarithm I can rewrite as multiplication outside the logarithm. And so I just expand this thing completely. I split it into as many logarithms as I can. Exponents go out front, and now this thing's expanded. All right. With the next one, there's a couple different ways that I can do this. There's 2 different ways that really I can approach this. I could bring that first 3 out front, and that would give me this, log base 2 of x to the 5th y squared. And now from here, I could split that logarithm into addition of 2 separate logarithms. That's an ugly looking 5. Let me try that again. I can't live with that. And now from here I can bring each of those exponents out front in front of their respective logarithms. So that's going to give me a 15 log base 2 of x plus 6 log base 2 of y. The other way to approach this one, the other way we can think about this, is really I could simplify what's inside here first. If I'm raising that to a power, I multiply the exponents. So if I just rewrite this, it would end up being log base 2 of x to the 15th y to the 6th using my rules of exponents. And now from here, using my properties of logarithms to expand, it splits into log base 2 of x to the 15th plus log base 2 of y to the log base 2 of y to the 6th. And now I can bring each of these exponents out front. And you'll notice right away that I get the same answer, just two different approaches to the order in which we do this. Okay? If I take a look at the next one, for these it says to evaluate each, and I can evaluate some of these by hand if the numbers work out well, but most of the time I'm just going to be evaluating these on the calculator. And so for this one, there's no relationship that we can immediately see between 98 and 7, so I'm just going to plug this one into the calculator, so I use my change of base, so I do the natural log of 98 divided by the natural log of 7. So again, it's the natural logarithm of what was inside there over the natural logarithm of the old base. And when you plug this into your calculator, just make sure you close those parentheses around the 98 before you hit that divided by the natural log of 7. And when you do this, it gives you approximately we'll say 356. I'll go 3 decimal places this time. Okay? If I look at the next one's one that I could do by hand. If you recognize it right now, 125 is 5 to the 3rd power. Whoops. And missed my 3 here. And what happens is log base 5 and the 5 cancel each other out, so this one's actually just going to give us a 3. If we were to plug this into our calculator, we just do natural log of 125 divided by the natural log of 5. And that'll also give us a 3 as long as we make sure we close those parentheses correctly. Alright? This one, it looks like it might have a relationship, but it does not, so I'm just going to plug it into the calculator. Natural log of 6 divided by the natural log of 3. Again, just make sure that you are really careful in terms of the parentheses here. Make sure you close the parentheses around the 6. It's usually the biggest issue with these. And you get something that looks like a 1.631 to 3 decimal places. Okay? If I look at this one, we want to solve each of these. Remember, when we're dealing with a logarithmic equation, we have to isolate the logarithm, but our version of isolating the logarithm here means rewriting it as one logarithm using our properties, all right? So here I have 2 logarithms being added. It becomes multiplication inside the logarithm, so it's log base 3 of. When I multiply, that gives me an x squared plus 6x equals the 3. And now to undo log base 3, I have to do 3 raised to the power of each side. Remember, this is where I do 3 raised to this power equals 3 raised to this power. Basically, each side of the equation becomes the exponent. And so what I have is 3 raised to the log base 3. They cancel out. Over here, I have 3 raised to the 3rd power, which gives me a 27. So I end up with x squared plus 6x equals a 27. And now from here, I want to solve this quadratic. I'm going to subtract the 27 from each side. That's going to give me an x squared plus 6x minus 27 equals 0. I'm going to solve by factoring, so I build a bridge and I factor this one. This factors into an x plus 9 and an x minus 3. And now I set each factor equal to 0. So I end up getting 2 answers here. The first answer is x equals a negative 9. The second answer is x equals a positive 3. But when I try to plug these back in, remember, negatives don't work when we try to plug them into a logarithm. So the only valid answer that I get here is the x equals 3. The negative 9 ends up being an extraneous solution. Okay? If I look at this one again, I want to rewrite it as one logarithm first. So this becomes log base 4 of. Subtraction becomes division inside the logarithm. And now to undo log base 4, I have to do 4 raised to the power of each side. So I do 4 raised to this power equals 4 raised to this power. Over here, log base 4 and the 4 cancel each other out. On the other side, I have 4 to the 2nd power, which is 16. And now from here, I multiply each side by 5 to finish solving this thing. Or you can cross multiply on this one. but I end up with x equals 80. And that's it. And that's a valid solution. I can plug that back in and it'll work just fine. All right. If I look at the next one, I'm going to do essentially the same thing. I combine these into one logarithm, so it's going to be log base 5 of. This one is going to be an x squared minus 4 over. Let me fix that parenthesis up. I got a little carried away here. Over the x minus 2. And it's all equal to the log base 5 of 8. And now in order to undo log base 5, I have to do 5 raised to the power of each side. So I do 5 raised to this power equal 5 raised to this power. Over here, log base 5 and the 5 cancel out. Over here, they also cancel out. So what I'm left with is an x squared minus 4 over x minus 2 equals an 8. And now from here, I want to solve this thing. I'm probably going to write this as 8 over 1. And now you can cross multiply. So I cross multiply, I get 8x minus 16 equals x squared minus 4. I got to get everything on the same side of the equation, so I'm going to subtract the 8x and I'm going to add the 16. And so what happens here, let me rewrite this guy up here, that's going to be an x squared minus 8x plus 12 equals 0. Now I'm just going to try solving this thing by factoring. So I build a bridge, two numbers that multiply to a positive 12 but add to a negative 8. Looks like it's going to be a negative 6 and a negative 2. So x minus 6 and an x minus 2 equals 0. I set each factor equal to 0. That got a little bit too close. Let me scoot that guy over. And now I solve each. Here I add the 6, so I get x equals 6. Here I add the 2, so I get x equals 2. And then you plug these back in, make sure they work. And what happens is we're going to find out that when we plug the 2 in, I get log base 5 of 0, which I also can't do. Remember, the thing inside the logarithm has to be positive. It can't be 0, it can't be negative. So this 2 ends up being an extraneous solution. So just be aware of that. You can't get negatives when you plug into the logarithm. You can't get 0 when you plug into the logarithm. And this one does give me 0 when I plug it into the logarithm. Okay? So the only valid solution here is the 6. Okay? If I take a look at the next one, it says to solve each, and we want to round to 4 decimal places. So when I look at this, when I just have a single exponential piece of the function, here I just have the 7 raised to a power. So there's only one exponential piece. The best thing to do is just to match the base when we take the logarithm of each side. Unlike the examples we did previously on the first page, I can't get a common base here in terms of the exponents, so I have to solve this using logarithms. But I'm going to use a logarithm of the same base. So I do log base 7 to this side. Whatever I do to one side, I have to do the other side. And so what happens here is the log base 7 and the 7 cancel. So I'm left with the x minus 5. Over here, this is going to be a job for my calculator. I'm going to plug in the natural log of 100 divided by the natural log of 7. And that's how I'm going to come up with that logarithm. I'm just plugging it into my calculator. And then I just add the 5 to each side. All right. So when you do this, again, just be careful as you plug this into the calculator. Make sure you punch that logarithm in first. So I want to do the natural log of 100 divided by the natural log of 7. Again, make sure you close the parenthesis around that logarithm. And that gives me 2.366589 something. All right. Then I'm going to add the 5. And when I do that, it gives me a 7 point. And to 4 decimal places, that's a 366. And then the 58, so it rounds up to another 6. And that's it. Okay? Number 14, this process becomes a lot more complicated because unlike number 13, we just had a single exponential function, so it was easy to kind of match that up with 7 raised to the power with log base 7 and cancel things out. Here we have 2 exponential pieces. Granted, each one of those is by itself, which is a good start, but the first side of the equation would be nice to use log base 5 to cancel out. The second side would be nice to use log base 8 to cancel out. So when I'm caught between trying to decide between 2 different bases, what we do is we don't choose. Instead of choosing either one of these, what we're going to do is we're just going to take the natural log of each side. Okay? So instead of choosing one of the bases and making one side happen, the other one disappointed, we're just going to disappoint both of them by taking the natural log of each side. So I'm just going to do the natural log of each side. And any logarithm can undo an exponential function because it allows us to bring the exponent out front. So we use this property where we bring that exponent out front. Scooted that around just a little bit. On the other side, I do the same thing. I bring the exponent out front, so the 2x comes out front. And now what I have to do is I've got to distribute this natural log of 5 to each of these. When I do the distribution here, it just becomes x natural log of 5 plus 2 natural log of 5. Over here, I still have the 2x natural log of 8. And now from here, I have to get all the x's on the same side and everything else on the other side. So for this one in particular, I'm going to go ahead and subtract the x natural log of 5 from each side. And when I do that, on the first side I'm left with a 2 natural log of 5 equals. Over here I'm left with 2x natural log of 8 minus x natural log of 5. And now to get x by itself, because I don't want to plug this into the calculator yet, I want this to have a lot of accuracy, so I want to wait till the end to plug it in. What I'm going to do here is I'm going to factor out the x in order to get it by itself. So I factor out the x. This is a 2 natural log of 8 minus the natural log of 5. And now I have to divide by this whole thing that's in parentheses. And there's a lot of different approaches to this in terms of using our properties of logarithms to simplify. Many of you probably simplify this as you go, which is probably the way I would do this one. But as we go to plug this into the calculator, we're going to find out that this is really difficult to plug in. And part of the reason for that is because of all the parentheses we're going to need. But keep in mind, simplifying using properties of logarithms, 2 natural log of 5, I can bring this 2 up as an exponent, all right, as part of my properties of logarithms. So that numerator can just become the natural log of 25. In the denominator, the 2 that's in front of the natural log of 8 can go up as an exponent. So that's going to give me the natural log of 64 minus the natural log of 5. And now subtraction, it can be rewritten as division inside one logarithm. So that entire denominator becomes the natural log of 64 over 5. And so what happens here is this becomes a lot easier to plug into my calculator when I use my properties of logarithms. All right. Again, most of us are probably going to use those properties as we go rather than waiting to the end to simplify using all these properties. But when we plug this into the calculator, it looks like it's going to give me a 1 point, let's see, we want 4 decimal places, 1.2626. And that's it. Okay, so just be really careful as you punch this into the calculator. Use your properties of logarithms to simplify this, make it a little bit easier. All right. If I look at the next one, it says an investment of $1,000 is earning 8% APR compounded quarterly, and we want to find the number of years needed for the investment to double. All right. So it's an investment, so we're talking about growth. So we need to decide between the standard model and the continuous model. Because it's APR and it's compounded quarterly, it means that I'm waiting for the quarter to end before I get my money, so the increases are happening on specified time intervals. So I'm going to use the standard model, the y equals a times 1 plus r raised to the t. Remember, the big thing here, the big issue is we have to make sure that the units match. All right, and right away in the description of the problem itself, we have 2 units that do not match. All right, I've got APR and it's compounded quarterly. All right, so if it's APR, that's 8% per year. We need to know what is that per quarter. So if we think about it, 8% for the year, that's 0.08. That's for the year. We got to divide that by 4 because we want to know what it is per quarter. So it becomes 0.02 per quarter. All right. See, that forces the units to match. So when I plug this in, the initial amount is 1,000. The rate that we're going to use is 0.02. And I want to know when this thing is going to double. So time is the thing that we don't know. I want to know when this equation is going to equal 2,000 though. And now I can solve this thing for t. So again, I have to divide. I have to get the exponential part by itself, just like we did in the previous examples. You always want to get that thing by itself, so I'm going to divide each side by the 1,000. So I'm with 2 equals, that's going to be a 1.02 raised to the t. And now to undo the exponential function, I have to take the natural log of each side. So I'm solving the same way I did the previous couple examples. When I do that, I end up with the natural log of 2 equals. Over here, I can bring the exponent out front, so it becomes t times the natural log of 1.02. And now I just have to divide each side by that logarithm. So I divide each side by the natural log of 1.02. Whatever I do to one side, I have to do to the other side. And now it becomes a job for my calculator, so I'm just going to go ahead and plug this in. So it gives me about a 35. And again, the units here are really important. This is 35, but it's 35 what? Well, since my units here in terms of the percentage were per quarter, it means my time is coming out in quarters, which is kind of a weird measurement here. So I'm probably going to convert that, divide it by 4, change it back to years. It's 8.75 years. All right? So be very aware of the units here. I want to know at how many years this thing is going to double. Well, keep in mind that my time comes out in quarters because my percent was in quarters. So the units have to match. Be very, very aware of those units. Okay? If I look at the next one, it says a new car costs $22,350, depreciates at 20% per year. I want to know how much the car is going to be worth in 10 years. All right? So again, this is my standard model for decay, and it's decay because the rate is going down. We reevaluate it each year, so that's when the major decrease happens. So I'm going to use my y equals a times 1 minus r raised to the t. Okay? And now I just plug in what I know. I know the initial amount was $22,350. I know the rate is 20%, and that's per year, and my time is in years, so the units are going to match here. That's 0.2 raised to the t, which is 10. And now really this is just a job for my calculator. I plug it in and see what. So I find out that the car is worth $2,399.81. And because we're talking about money, we're just automatically going to round to 2 decimal places. All right? So then the question is, when will the price of the car be $5,000? Maybe I want to wait for this thing to drop to a certain price so that I can afford it. So I start off the same way, except now I'm going to set this thing equal to $5,000. The initial amount is still the same. The depreciation rate is still the same. The only difference now is I want to solve for time. I want to know when. Okay? And so from here, I want to solve this thing. I'm going to divide each side by the 22,350. When you do this division, this division is probably not going to work out very nicely. And again, I want to wait till the end before I start rounding anything off. So I'm going to leave this as a fraction. And you don't even have to reduce this fraction. Maybe you'll do some simple reducing, like you'll cross out the zeros here. But you don't have to simplify this thing all the way. You can just leave it as a pretty big, ugly fraction. And it's not going to matter because we're going to be punching this thing into our calculator in the end. All right? So I'm going to leave it like that. Not even bother to simplify it the rest of the way. Equals, over here I get a 0.8 raised to the t. And now from here, if I want to get that exponent down, I got to take the natural log of each side. And this is why I didn't bother reducing it. I'm going to be punching that logarithm into my calculator when it's all said and done. So I have the natural log of, separate those a little bit, 500 over the 2235 equals t times the natural log of 0.8. And now from here, I just have to divide each side by that logarithm. All right, and then once again, it becomes a job for my calculator. I just have to plug this thing in to see what t is going to equal. And keep in mind that t is going to come out in years this time. So I plug it into my calculator, and it looks like it gives me approximately 6.71 years. All right, and that makes sense based on the previous information that I have. After 10 years, it was down to about $2,400. So yeah, after about 6 or 7 years, it's probably going to be down to about that $5,000 mark. Okay. If I look at the next one, it says a zombie horde has an initial population of 400. After 12 hours, it's grown to 1,542. And the first question is, how many zombies are there when time equals 0? Keep in mind that time equaling 0 is basically where we start, all right? Time being 0 is the beginning, and the beginning is essentially the initial amount. This is just trying to get you to understand that the initial amount is 400. That's when time equals 0. That's where we're starting, okay? The next piece says, what's the growth rate constant of this particular strand? Because this one is growth, and it's a continuous growth here, because these things aren't going to stop, it's going to constantly be growing, I'm going to use this formula, a times e to the kt. And from here, it asks me to find the growth rate constant. It's asking me to find the k value, all right? So I start with the initial amount. The initial amount was 400. E is the number e. K is the thing I'm looking for, and then what it gives me here, it gives me a time of 12 hours. So if I plug the 12 in here for time, well, after 12 hours, this equation, this whole thing is going to equal 1,542. All right, so it's basically saying, all right, when time equals this, the equation equals this. Now I can solve for what's left. I can solve for that k value. So I'm going to divide each side by the 400. Again, just like before, I could punch this in my calculator and see if it works out nicely. This one might work out okay. Yeah, it does. This one works out all right, so I'm going to leave it as a decimal. The thing I don't want is I don't want to write a decimal that I have to round off. This one you could easily leave it as a fraction. It wouldn't be a big deal. Okay, equals e to the 12k when I multiply that. And now I just take the natural log of each side. The nice thing about this formula is when I take the natural log here, natural log and the e completely cancel each other out, which means I'm left with the natural log of the 3.855 equals just a 12k in this example. So instead of having to divide each side by logarithm, I just have to divide each side by 12. And now that's going to give me my k value. All right. And for this k value, we'll round it to quite a few decimals here, see what we come up with. For this one, I'm going to go ahead and do, I'll just do 4 decimals for this one. And keep in mind, depending on where you round this thing, your answer might be slightly different from mine. We've been doing 4 decimals quite a bit, so I'll stick with 4 decimals for this one. And keep in mind that that is per hour because my time was in hours. All right? It's really important to kind of make sure you understand the units that are attached to that. So then when I approach this next one, it says, what's the population after 3 days? Well, in this one, I start off the same way. The initial amount here is going to be the 400. E to the 0.1124 multiplied by time. Well, because my k value was per hour, my time now has to be in hours. All right, so I can't plug in 3 for time. I have to plug in 72 for time. All right, it's got to be in hours because my constant rate was per hour. And so this one's just a job for my calculator. So it looks like I come up with 1308.24. All right, and I'm going to go ahead and leave that on there because I think we can have 0.24 of a zombie. Okay, so again, I label it, make sure I know what I'm talking about here. All right. In terms of this one, it says when will the population reach? That comma is in the wrong place, obviously. It should be 1 million. Poor choice of putting a point there. But anyway, 1 million. Basically, I'm going to start off the same way. I still have this k value that I found. I want to know when this thing is going to equal 1 million. 400 is still the initial amount. E to the 0.1124 times t. T is now the variable. I approach this almost exactly the same way as I did the problem above. I divide each side by that 400. It's just like when I solved for k. So when I do the 1 million divided by the 400, it gives me 2,500. So I get 2,500 equals e to the 0.1124 t. And now from here I have to take the natural log of each side. Once again, the nice thing about this equation is natural log and e completely cancel each other out. So I'm left with the natural log of 2,500 equals that 0.1124 t. And now I'm going to go ahead and divide each side. And once again, there's no logarithm here that I'm dividing by. I just divide each side by the 0.1124 and come up with my t value. Which in this case, it looks like a 69.6. And again, that is in hours. Okay. In this one, it says a virus is wiping out the human race, and after 1 week, a town with an initial population of 133,427 people now only has 109,406 people left. And we want to know what the population will be after a year, okay? So the first thing we need to do is come up with the decay rate constant for this one. Because it's decreasing, we know it's the decay rate constant. I know it's continuous because viruses work that way. Really, any biological example we have is going to be that. Remember, the only difference in terms of the equations is we get that negative sign in front of the k value. So now from here, I just plug in what I know. I know the initial amount was the 133,427. The other piece of information they give me is time and then a population that goes with that time. So the time that it gave me was 1 week. So I'm going to plug a 1 in for this thing. And if I plug a 1 in there, it means this thing is going to equal 109,406. And now from here, I can go ahead and solve for k. And really, there's different values you could have used for t here. If you used 7 for t, you're going to get a completely different k value. But your k-value is going to be per day, so your end result should be pretty close to mine, all right? So keep that in mind. So I'm going to go ahead and solve this thing. I divide each side by the 133, 427. And again, that might not work out nicely on my calculator, but that's okay because I can just leave that as a big giant fraction. In fact, maybe I'll do that for this one just so you can see it. When you do this, just leave it as a big fraction. Just leave it as the 109, 406 over the 133, 427. All right? There's no need to punch it into the calculator. There's no need to even simplify this thing because my next step, in order to undo the exponential part of the function, I'm going to take the logarithm of each side. So I take that logarithm of each side over here. The natural log and e cancel out. So I'm left with the natural log of 109, 406 over the 133, 427 equals a negative k. And now I'm just going to divide each side by that negative 1. All right. So it becomes a job for my calculator. I'm just going to go ahead and plug this in. And it told me to round this to 3 decimal places. So I'm going to go ahead and plug it into the calculator. So I end up with a k value of 0.198. Okay, and that's per week because my time was in weeks. And if you happen to get a negative k value here, it just means that you missed the negative sign when you first wrote down your problem. So now I'm going to use that k value and I'm going to plug it in to make this prediction. I want to know how many people are going to be left after 1 year. So I start with the same initial amount. So the initial amount here is the 133, 427 e to the negative 0.198. And after 1 year, keep in mind that that k value is per week, so my time has to go in weeks. There are 52 weeks in a year, so I do 52 here. And now once again, this is a job for my calculator, so I just plug this thing in. And it looks like it gives me 4.5 people. All right, so I'm going to have around 4 or 5 people left. Maybe we would round this to the nearest whole person and say there's going to be 5 people left. Okay, but not many. This thing is wiping us out. Okay? If I look at the next one, it says scientists want to determine how old Superman is. All right, so they know that when he came to Earth, there was kryptonite with him, and what happens is as soon as we entered Earth's atmosphere, the kryptonite began to decay and has a half-life of 300 years. So if the original sample there was 4,200 grams of kryptonite with him, and now there's only 3,500 grams of the substance left, so there's only 3,500 grams left. We want to use this to determine how old Superman is. All right. So the first thing I need to do is I need to convert half-life into a k value. All right. So keep in mind, once again, this is decay, and it's continuous decay, so we're using this model. But I'm just going to convert that half-life into basically a k value here. They're both describing the same thing, but I need the k value to work the equation. So the initial amount was the 4,200 grams. K is the thing I want to convert here. And when I'm talking about half-life, the half-life is 300 years, so if I use 300 for the time, the half-life is how long it takes to cut this thing in half. So after 300 years, instead of 4,200 grams, I'm going to have 2,100 grams. Okay, I'm going to have half as much. So now I'm going to go ahead and solve for the k value, so I divide each side by that 4,200. And that's going to give me a 1/2 equals e to the negative 300k. Now I take the natural log of each side, like I always do. Over here, the natural log and e cancel each other out, which is wonderful. So I'm left with the natural log of 1/2 equals a negative 300k. And now I just have to divide each side by the 300, or the negative 300 rather. When I do that, again, it's just a job for my calculator. If you happen to get a negative answer here, it just means you forgot the negative and missed the negative 300. And to 5 decimal places, this is going to be a 3-1. Okay, so 0.00231. And because that was in years, this is per year. Which means when I start doing this calculation, the time is going to come out in years, which is kind of what I want anyway if I want to determine his age. We're assuming that he was very young. He was just a baby, maybe only a couple months old when he got sent here. So from here, I want to predict how old he is. So I start off with the 4,200. This is all very scientific. Negative 0.00231 multiplied by time, which is the thing I'm looking for, and I want to know when this is going to equal when the substance is down to 3,500 grams. Okay, so now I can just go ahead and solve this thing. I divide each side by 4,200. Again, you don't have to reduce this. You would probably at least reduce it to this much, the 35 over 42. Yeah, it reduces more to reach divisible by 7. But let's just leave it like that for now. We're going to be plugging this into the calculator anyway, so it doesn't really matter that much. And now from here, I just take the natural log of each side. Here, the natural log and e cancel each other out. So I'm left with the natural log of 35 over 42. Again, if you had simplified that to the 5/6, that's fine as well. Over here you get the negative 0.00231t. There's no logarithm left, but I just divide each side in order to solve this thing. And now it's just a job for my calculator, so I go ahead and plug it in one more time. So I get 78.9 years. So Superman is approximately 79 years old, so he's kind of an old fart, but he's in pretty good shape for an old guy, so he can move for a geezer. All right, so good for him. All right, hope this is helpful and good luck on your test.